So I'm Jean Lapierre. I'm a Senior Director of Advanced Technology for Matrox. I'm also one of the co-chair of the VSF working group on IPMX. And today we're going to talk about the Internet Protocol Media Experience, or IPMX. So IPMX is a AV over IP transport, discovery, and control protocol. It's aimed at the Pro AV market, but it's based on ST2110 and AMWA NMOS. It's being developed, like I said, by the Video Service Forum. And by the way, ST2110 was also originally developed by the VSF. So the main components of IPMX are the RTP transport protocol is based on ST2110. We have a component for handling HDCP protected content, and that's based on the Digital Content Protection LLC specifications. We have a FAC support, and that's based on SMPTE ST 2022-5. The discovery and query is based on NMOS ISO4. Control plane for IPMX is based on AMWA NMOS ISO5. And the EDID management of HDMI is based on AMWA NMOS IS11. So TR10 is basically the RTP protocol for TR10 is documented as a series of differences between 2110 and IPMX. So TR10, much like ST2110, is divided into multiple documents that cover each part of the protocol. So in TR10, which is the IPMX spec we're working on, there's a document called TR10-0, and basically that's the map of what's in TR10. So it describes with each document and what is inside each of those parts. These are the different parts of TR10. There are several of them. We'll go over each of them individually. They are published at this URL on the VSF site. If you're looking for the document, you basically Google VSF IPMX. You're going to end up on a landing page for the working group, and you'll see my picture and a picture of my colleague, Chair. And there's a link to download the specification. So VSF TR-10-1. The first document, it's the timing spec. It's where most of the differences between IPMX and ST2110 are located. And today we'll spend most of our time in that specification. So TR-10-1, the timing spec, let's cover the first part about PTP. So IPMX works on networks that have PTP and networks that do not have PTP. So when there's PTP on the network, IPMX uses PTP the same way as ST2110 uses PTP. So it uses it for its common reference clock. Each device synchronizes its internal clock to the PTP, and the device will report in its SDP that it's using PTP as its reference clock. When there's no PTP on the network, which is specific to IPMX, each device uses its own free-running internal counter, and then it reports that it's using a local reference as the reference for the RTP timestamps. So in IPMX, because we're aiming at the Pro AV market, in Pro AV, most signals are not gen-locked, like a computer HDMI output that doesn't have a gen-lock. And so we call that an asynchronous signal. 2110 was designed mostly for broadcast use to replace SDI over IP. And in broadcast environment, everything is gen-locked together. And the signal on the AV network, the 2110 signal, are gen-locked. We call those signals synchronous signals. And so if we look at the RTP timestamp in 2110, because everything is synchronized and gen-locked, there's a direct relationship between the RTP timestamp and the PTP time. It's like at the beginning of the world when PTP time was 0, the first frame of every standard frame format started at 0. The RTP timestamp was 0. And then it goes up by exactly 1/50th of a second, 1/60th of a second. The RTP timestamp matches the PTP. So there's a direct relationship. It's actually a mathematical relationship. If you tell me what time it is in PTP, I can tell you exactly where inside the frame you are. That's 2110 synchronous signals. In IPMX, when we deal with a synchronous signal, there's no direct relationship. You can see on the graph here that for 25 frames of video, because the RTP timestamp work at a 90 kilohertz clock, you'll have exactly 90,000 ticks of the RTP clock for those 25 frames, but that won't necessarily match with a second of real-time PTP time. And so because there's no direct relationship between the two, we need a way to communicate to devices what the relationship is between our RTP timestamp and the reference time on the network. So even if we're on a PTP-enabled network with IPMX, because the signal is asynchronous, we kind of want to send the information that says, well, you know, this RTP timestamp corresponds to this PTP time. And to do that, we use RTCP sender reports. We didn't invent those. Those are part of the RFC 3550. Actually, when they developed 2110, they looked at RTCP sender report and they said, well, our relationship is fixed, so we don't need those. So they did away with them. But in IPMX, because we want to be able to support this asynchronous, we use RTCP sender report. And it's basically a little packet, a message that says, by the way, this is the time it was when I generated this RTP timestamp. And so it looks something like this. So as a small packet, it has different info in it. The one that's interesting to us is this is where we stick the time that was the time at which the RTP timestamp got generated. And this is a piece that says what the RTP timestamp was. Next thing I'd like to look at is traffic shaping. And so the model for the VRX model for IPMX is different than the 2110 one. In 2110, because the relationship between time, PTP, RTP timestamp, and how the receiver consumes the data, it is based on an offset from the PTP time. And so they can do that, they can afford to do that because there's a fixed relationship. Because we don't have a fixed relationship, we have to use a different method. And so in IPMX, what we do is we say the receiver will start to drain the VRX buffer when it's half full, not when there's a specific time, not at a specific time. And so the transmitter, in that respect, doesn't have a critical time at which it needs to start transmitting the first packet. It can start to transmit the first packet when it's ready. However, as soon as it starts transmitting the first packet, it has a fixed amount of time to transmit the full frame. We do that because we want the receiver to be able to consume the data and be sure that it's not going to starve when it reaches the end of the frame to display the frame. So the transmitter has to respect that total time to transmit the frame, but it still has to respect what we call the network compatibility model of 2110, which is there to ensure that devices don't burst a whole bunch of packets and overwhelm the switch. So there's a parameter that controls that, and IPMX uses the a wide sender value for the network compatibility model. And so the receiver itself in IPMX, we're interested in having the lowest latency possible between the transmitter and the receiver. We want to be able to enable that. We also want to be able to emulate like an HDMI cable. In HDMI, if the computer is outputting the signal at, say, I don't know, 59.2 frames per second, and then the monitor will display it at 59.2. There's not going to be any frame repeating or skipping or anything. It's just going to consume the data at the speed that the computer is outputting it. And so we want to be able to do the same thing with IPMX. So we provide all the information to the receiver that enables it to consume the packets that are coming in exactly at the same rate that they're going into the transmitter. And so if we look a little bit what that means, here we see on this graph, we see a transmitter that's very well behaved. This is most likely a piece of hardware converting from an input video to output. And we can see the transmitter waits a little bit and then it starts to send packet. Let's pretend here that once it's sent a few packets, the receiver starts to consume, all right? So the receiver starts to consume when its buffer is full enough. And it starts to consume and display those packets at the bottom. We have the receiver doing that. And you can see that I've marked the active video portion of the signal that was coming into the transmitter. The same amount of time from the moment the transmitter starts to transmit at the end of the TX delay. This dashed line over here shows by what time the transmitter has to be finished. You'll notice that the receiver because the receiver will wait a little bit before it starts, it kind of ensures that it's not going to starve and it's going to be able to display the data. And you can see that the latency between the initial signal that went in to the time that we're displaying is very, very small, which is one of our goals. Another transmitter example I give, maybe this is the same thing, but there's a piece of software or the hardware doesn't have to be so stable in how it transmits the packet. So I made it a little bursty. Now, the burst of packet that it's doing have to not be bigger than the Cmax value of wide, so that's fine, it's doing this. And the receiver starts when it has enough data, the same amount of data of my previous graph. And the transmitter starts at that time and it has this amount of time to do what it needs to do. And again, the receiver won't starve and they'll be able to still have to do a small latency. In this case, it's even a smaller delay. All right. Moving on to SDP file. What's the difference between TR-10 and ST2110 for SDP file? Well, basically, IPMX uses all and supports the same data that's in the 2110 specification. We add a few things. We add a tag that says, by the way, this is an IPMX transmitter. And then we add a few extra parameters that are used to help the receiver understand the timing of the sender so it can match it better. Link offset delay is a concept that was introduced in 2110-10 in the latest flavor that got published, I think, at the beginning of this year, 2110-10 2022. It's something that is listed in AS67, and it's about controlling the delay on your receiver to enable you to move the position of your output on your receiver. So IPMX supports that, and what we did is we added for devices that have a link offset delay capability, they need to use ISO 5 to enable control of it. So we added the control plane for link offset delay in IPMX. All right, that's TR-10-1, the timing spec. So if we look now at the different other parts, we have TR-10-2 that roughly corresponds to ST2110-20. This is the spec that explains how to packetize uncompressed video in the RTP stream. And so TR-10-2 basically reads as every part that 2110-20 that apply to IPMX are listed. And then for things that don't apply, it's basically a series of replacing. I basically did a search and replace of 2110-10 and replace it by TR-10-1. So basically changing the timing to be IPMX compliant instead of 2110 compliant. So we also added the fact that, okay, so in 2110-20, it explains if you're doing YUV, this is how you do it. If you do RGB, this is how you do it. It's like a big recipe book on how to do all these various things. But it actually doesn't tell you that 2110-20 has to support YUV. And for us in IPMX, because we wanted to support computers and cameras and everything else that is popular in Pro AV, we actually spell out that a receiver has to support YUV and it has to support RGB, both. Transmitter can do what they want. All right. And of course, we have our RTCP sender report, but we did add something to RTCP sender reports. We added an extension for IPMX. We're going to talk about the one for video here, but it also applies to audio and some other of the payloads. So what it is, the extension we did is it describes the stream that's associated with the RTCP sender report. So basically, RTCP sender report are sent right before every frame of video for video. And they have this timing information we saw before, but it also includes a description of the stream itself. And there's also in that, in that extension, we put a counter. And we'll see what the counter is used for. So the workflow we're trying to cover with that is an example of this podium here. If this laptop was transmitting an IPMX signal onto a network, and this monitor would be connected to IPMX and would be decoding it, I'm currently sending, let's say, 1080p, and everything is good. The monitor is displaying it and everything. And then someone comes and changes the resolution. Now, in 2110 and in NMOS, they're designed to establish connections and then for NMOS to be omnipresent, to realize that things are changing and reconnecting when things are changing. When I have an HDMI cable connected to a monitor and I change the resolution, the monitor just adapts and changes. I don't need to come with something else to tell it to do that. And so we needed something to handle that use case. All right. Our extension looks like this. We have a piece of it, which the media info block, that describes the media that the RTCP sender report is attached to. And we have this block version, which is really a counter. Let's see my example. Maybe graphically, it'll be easier to see what I was explaining. So here I have my display, I have my receiver, my sender. I come to the room. I connect my laptop to my sender. It starts sending to my network. Now I have to use an ISO5 command to tell my receiver, hey, I would like you to receive this signal. This part here is the SDP file. This is how NMOS works. It passed the SDP file to the receiver. It extracts all the info it needs. It's now receiving the signal. This is done to establish the connection. Let's say I'm an integrator. I just set up this room. I did this connection. I unconnect my laptop. I walk away. I leave it like this, just like I would have connected the HDMI cable. Everything's happy and working. I have my signal flowing. Everything is great. Then somebody comes on the laptop and say, hey, I really want to do UHD. And so he changes the resolution to UHD. I am now outputting onto a network a UHD signal. The RTCP sender report are sent right before every new frame of video that correspond. I painted gray the RTCP sender report corresponding to 1080, and in orange, the RTCP sender report that corresponds to UHD. So when that first orange one that's highlighted shows up, the block version counter I was showing you before is now different than the one in the gray. The receiver sees that it's changed. It goes, oh, something changed in the media block. Let me go see. Oh, the resolution is changed. The receiver can now prepare to receive this new signal, change the resolution on the monitor, and I have now a picture again that's UHD. And I didn't have to ask the integrator to come back to fix up the fact that we've changed resolution. And so this is very important for Pro AV, and the reason why we did this. So now everybody's happy doing HD. Somebody comes, changes a new laptop, same thing happens. That's the concept. TR-10-3 is the audio spec. It corresponds to 2110-30. Again, describing which part of dash 30 apply to TR-10-3, replacing all references to 2110-10 by references to TR-10, references to 2110-10 by reference to TR-10-1. We did put in that the minimum requirement would be that you'd have to support stereo 48 kilohertz, 16-bit, and 24-bit. And again, RTCP sender report for audio like we just discussed. TR-10-4 is the equivalent to 2110-40. Again, a series of differences between the two, which is basically this part apply, and for those part, refer to TR-10-1. Most of these specs, by the way, are 1 or 2 pages. They're very simple. TR-10-5, that's a new one. This is how the IPMX, what we had to introduce to IPMX in order to add support for HDCP protection, protected content. In Pro AV, there's very often use of HDCP protected content, and the Digital Content Protection LLC have specs that explain how to do HDCP over an IP network. The latest adaptation amendment covers how to do it with RTP, which is what IPMX is. But even though they explain how everything works and what the protocol should be and everything, they did not include the actual protocol for exchanging keys. So that's a critical point, because if Matrox, for example, would make a device and Manica would make a device, if we don't use the same protocol to exchange the keys, it's not going to work. And so we needed a standard way of describing it and providing it for everybody. And so this is TR-10-5, its key exchange protocol. Like I explained, it's based on a standard spec for the consortium that explains how to do that. We just add control and management to it. TR-10-6 is our forward error correction document. It is based on 2022-5. 2022-5, much like 2110-20, says you can do FEC, and here's all the different ways you could do FECs. Basically, in IPMX, we wanted to aim at much interoperability, and so we picked a very specific subset that we thought was sufficient for our needs. So we're saying it's 2022-5, this profile, that way. It's and it provides us protection for losing 2 packets every 232 packet, which in modern network, modern equipment, even RJ45, Cat5 base is sufficient. And it's simple. So that's our TR-10-6. TR-10-8 is our NMOS requirement specification. So it basically says if you're an IPMX device, you have to support NMOS, and these are the piece of NMOS that you shall support. It covers ISO 4, which is the discovery and registration part of NMOS. We talk about having to support DNS-SD, but also MDNS, and how the workflow should work, how you should behave when there's DNS-SD, but not MDNS, and things of that nature. It specified that you have to support ISO 5 for control. ISO 5 is how I'm routing a signal from a sender to a receiver, telling the receiver, as we saw, that command. And finally, it also includes this new API that we added to ISO 5 for controlling the link offset delay. TR-10-9 is our work in progress. It hasn't been published yet, but it will cover system environment, device behavior, things about how to deal with network support, DHCP, IPv4 support, how you should behave around that. Things like actually specifying that how to align the video with the audio so you have lip sync. Believe it or not, in 2110, all the tools are there, but it's not a hard requirement. They just suggest that you should do this. So TR-10-10 is the HDMI InfoFrame packet transport, also a work in progress. So in HDMI, there's a bit of the equivalent of VANG data. It's called an InfoFrame. It carries things like the similar things to what we would find in -40, but it works differently, so we had to have a specific document covering how to transport that. we're not quite finished with that one, so that's also a work in progress. And now we come to TR-10-11, which is constant bitrate video, basically the equivalent to 2110-22, where we transport compressed video that's a constant bitrate. Again, written as these are the part of -22 that apply to IPMX, changing all references to 2110-10 to TR-10-1. Sender reports are covered in there, including what data should be inside the info block. And finally, we have VSF TR-10-12, which is our AS3 transparent transport, equivalent to 2110-31. Again, just a list of differences and replacing TR-10-1 for timing, substituting that instead of 2110-10. Sender report, and that's it. And any questions? Wow, I was clear. Everybody understood everything. That's perfect.
Okay, I was going to give this.
Sorry. Sure.
Hello. So I've seen these in the last few days, learning a lot about NMOS, and also a gentleman from Ross Video stopped by and talked about Catena, right?
About?
Catena, is that pronouncing it correctly? C-A-T. It's Ross Video sort of interpretation of NMOS.
Oh, okay, okay.
Right, and I'm seeing this now, right? So how would I navigate and know like which is from the industry, which is from? I guess I'm saying like who's pushing the standard? How are these conversations being had between industry vendors and organizations like AMWA?
Okay, so at least for VSF, where I operate, right, it's industry people that are participating in defining the specs, right? So it's basically, different companies. There's vendors obviously in there, but there's also end customers that are participating in specifying this. AMWA is a little bit of a similar kind of organization. So in AMWA, they recognized that we needed a standard way of doing this control, a standard way to find devices on your network, right? And so they proposed an open specification for that, and like the EBU endorses that type thing. So it's like end customer, like TV station, they tell manufacturer, hey, you better support AMWA and NMOS, because that's what we want to use to control everything, because this way, every manufacturer has a chance to read the spec, implement it, and then interoperate, right? So IPMX, that's what we're all about. When 2110 was written, NMOS didn't exist yet. So they did not have the luxury of putting in their specification that you have to support NMOS. But when we did IPMX, we could. So that's what we did. So from IPMX point of view, what we're pushing is standard, based on standard. So we took 2110, we looked what was missing for Pro EV, we added it. And then we said, well, we better make sure we say you have to have AMWA to do the control, registration, and everything, right? Now, if other people decide that there's a better way to do it for their company, that's their company, right? So I can't really talk about that. Does that answer your question? Yeah. Thank you.
So can I ask you to continue that?
I think he's gonna want the mic.
All right. Yeah. So IPMX would seem so with AMWA they've got a test suite. There's tools you can test. Say, okay, this is what my product can do. It meets the standards. How does IPMX respond to that? I mean, is it more suggestive?
No. So there's obviously eventually going to be a test suite to validate that your device does IPMX properly. And among those things, it's going to probably actually for sure say you have to run the AMWA test and pass it, right? So that's the logic. And there'll be other tests. In 2110, we had the JT&M tested program. So IPMX is going to require something like that in order to be able to say, yeah, you do adhere to the specification and stuff. So we can be able to do that. Is that
Yeah,
good?
definitely. Thank you.
Thank you.
I guess I'll just ask if there's some place we want to get, like, is there documentation on kind of how to implement? It almost sounds like this is kind of like when you say standards on standards, it kind of sounds like this is sort of an opinionated standard on top of the more open standards of SMPTE and NMOS. Is that accurate to say, or not as much?
I wouldn't say that. I would
Okay.
say you look at SMPTE, and SMPTE lets you do A, B, C, D, right? And then that means that somebody may do A, somebody may do B, and then you as a customer, you buy the two equipment, you find out it doesn't work, right, together. So we looked at it like really closely, and we tried to write the specs so that where it wasn't, for example, if we take RGB versus YUV, right? If I said you could do YUV, you could do RGB, I have a transmitter that's doing RGB, a receiver that only does YUV, you end up with purple and green on your screen, right? So our spec says, no. As a receiver, you have to do both, right? And therefore, that means that when they plug together, it works. So it's more like looking at it and constraining it in a way that serves the industry.
I think it's great. I think that's what I'm thinking of, is in terms of opinionated. Like, I like the idea of like it must support this to kind of give some structure to the
Yes,
right.
yes. So it gives context, and it gives
Context.
a restriction that makes it useful, and interoperability is what IPMX is all about, right? So, all right. Well, thank you very much.